Hello and welcome to this video for Chemistry 30, the equilibrium acid-base unit. Today we are going to look at how to predict acid-base reactions. So it's important to note that in order to do this, we're going to be using the acids in the data booklet. There's a chart. I'll actually go to that chart right now. This is the chart, and it shows you again the name of the acids with the formula for the acids on the left, and on the right-hand side are the conjugate bases. Okay, the acids on this chart are written in order from the strongest acid at the top to the weakest at the bottom. And the bases are written in order, the weakest at the top down to the strongest at the bottom. So when you have an acid-base reaction very similar to electrochem where you're using the reduction table, you're going to pick the strongest acid, whichever one is closest to the top, and the strongest base, which one is ever closest to the bottom. Now, if the acid is higher than the base, just like in electrochem, this was called a spontaneous reaction, in this unit, we call it a product-favored reaction. So if it's product favored, above the equilibrium arrow, you can either write that it's greater than 50%, or above the equilibrium arrow, put a forward arrow as well. If the base is higher than the acid, so let's say we have something like the fluoride ion reacting with hydrosulfuric acid, then the base is higher than the acid. The reaction would instead be reactant favored, which means it's not happening greater than 50, it's less than 50%, or above the equilibrium arrow, you put a reverse arrow. Okay? So that's basically it. You pick the strongest acid, the strongest base, you transfer a hydrogen from the acid to the base, and make your products. So we are going to transfer only one proton, again the hydrogen with a 1+ charge, it carries that 1+ charge with it. So whatever is gaining the hydrogen, its ion charge is going to increase by 1. Whatever's losing the hydrogen, its ion charge is going to decrease by 1. So we're going to start by listing what we have present. If you have one of the top 6 strong acids on the data table, you ionize it into hydronium and the anion, only if it's a strong acid. Okay? If it's a weak acid, not one of the top 6, you do not dissociate it. You do not split it apart into ions. If it's an ionic compound, of course, you do ionize or dissociate it. And we're going to include water because, again, these are in solution. Then you're going to identify everything as being an acid or a base or both if it's amphiprotic. You're going to then pick the top left for the strongest acid and the bottom right for the strongest base and react them. Like I said, you're transferring the hydrogen ion from the acid to the base to predict your conjugate products, the conjugate base and the conjugate acid. Make sure you also label them. And then, like we talked about, put your position of equilibrium, whether it is product favored or reactant favored. So if we look at a couple of examples, it says that we are reacting sodium hydroxide with vinegar. Vinegar is acetic acid, and that would be given to you in the question. So sodium hydroxide is an ionic compound, therefore it's going to dissociate into sodium ions and hydroxide ions. Acetic acid is a weak acid. It's not one of the top 6. So that means it is not dissociating. It is staying a whole compound. And then water, which is molecular compounds also stay whole compounds. Okay? Now, your cation, like sodium, is nothing. It's not on the chart, so it's nothing. The only cations that you'll find on the chart is the ammonium ion and the hydronium ion. Those are acids. But every other cation, like sodium, is nothing. Hydroxide is the strongest possible base you can have. It's the furthest down on the chart on the right. Then you have acetic acid and water as possible acids. Water could also be a base, but we've already identified hydroxide as the strongest base. So when you check the chart, you should see that acetic acid is highest up on the left of the chart. So if we go back and check the chart, just to show this, we have acetic acid, which is right here, and the hydroxide ion, which is right here, okay? So acetic acid, again, being other than water, further up, so it's the strongest. And then other than water, again, for hydroxide's the strongest. Because my acid is greater than my base or higher than my base, this is going to be a product-favored process. So to write the reaction, we're going to show the transferring of the proton, and then we're going to write also labeling everything that we have. So my acid is acetic acid, CH3COOH. When you have an organic acid, remember the donatable hydrogen is bonded to the COO part of the compound. So that's the hydrogen that's going to go from the acid to the base. Now the base is the hydroxide ion. I'm also going to label that as my base. Then we show equilibrium arrows, and because this is product favored, a full forward arrow. When my hydrogen moves over to my hydroxide, it's going to become HOH with no charge because the hydrogen 1+ canceled the -1. So this is the conjugate acid of my base. And what my acid becomes, it's losing a hydrogen. So it's the COO -1 ion because it lost the positive that it had. So it now has a negative charge. It was neutral, it had no charge, now it's -1. Okay, connects the conjugate acid and conjugate base to the acid and base that it started from, because those are conjugate acid-base pairs, and that's what we're trying to show, the pair that they form. Okay. In the next example, we're going to use a strong acid. We have hydrochloric acid. Hydrochloric acid is one of your top 6 strong acids. So when I list what I have present, I ionize it into not just hydrogen, but hydronium, because the hydrogen ion will bond with the water to make hydronium, and the chloride ion. Ammonia is a molecular compound, so it stays whole, and I have water. Now listing, again, I'm just going on the chart, finding where everything is, picking the strongest acid and strongest base. So hydronium is the strongest possible acid you could have on the chart because all of the strong acids will ionize into it. Chloride is a very weak base. It's actually weaker than water as a base. So in our pH calculations, we would never consider it a base. Out of all of our bases, the one furthest down on the right is ammonia. So if I write my reaction, I'm going to react my strongest acid, which is the hydronium ion, with my strongest base, which is ammonia. And again, we're transferring the hydrogen, one hydrogen only. Even if there's multiple hydrogens in this section, we only transfer one hydrogen. This is a product favored process again because the hydronium is higher than the ammonia. The ammonia is forming the ammonium ion when it gains a hydrogen, so it has a +1 charge. That is now the conjugate acid of my base, and H3O positive becomes H2O with no charge and is now the conjugate base form of my acid. And that's it. Thank you for watching this video.